You probably think of the speed of light as just a big number in a textbook. 299,792,458 meters per second. Enormous, sure. The fastest thing we know, sure, but that's where most people stop. They hear nothing can go faster than light. They attach Einstein's name to it, and they treat it like a cosmic speed sign posted on the highway of the universe. That's not an explanation. That's a slogan. If you really ask why there is a limit at all, and what would happen if you managed to beat it, the answer is far stranger and much more disturbing than we don't have strong enough engines. Because the speed of light is not just about going fast. It is the line between a universe where causes lead to effects in a consistent order, and a universe where effects can interfere with their own causes. Cross that line the wrong way, and the thing that breaks is not your spaceship. It's causality. To see why, it helps to start somewhere completely different. Not with light, but with falling. Take an object near Earth and drop it. In 1 second it falls about 16 feet, assuming you ignore air resistance. That number comes from a very simple formula. Distance equals 1/2 times acceleration times time squared. Near Earth's surface, the acceleration is about 32 feet per second squared. Half of that is 16, so in the first second you get roughly 16 feet of drop. That's a down-to-earth measurement anyone can reproduce. Now point your attention at the moon. It circles Earth once every month or so. It doesn't plunge straight in. It looks like it stays up there. But if you pause the motion in your imagination, freeze the moon in place and take away its sideways speed, gravity would pull it inward. The orbit only exists because the moon is continually falling toward Earth, but always sliding sideways fast enough to miss. Newton noticed something crucial here. The radius of Earth is about 4,000 miles. The distance from Earth's center to the moon is about 240,000 miles. That's a factor of 60. If gravity weakens with distance, by how much? Suppose the strength falls off, like 1 divided by the square of the distance. Double the distance, 1/4 the pull. Triple the distance, 1/9. Multiply the distance by 60, the strength becomes 160 squared, equals 1/3600 of what it is at Earth's surface. If something near Earth falls 16 feet in the first second, then at the moon's distance the same gravitational law says it should accelerate inward, only enough to drop 16/3600 feet in that first second. 16 feet is 192 inches. Divide by 3,600 and you get about 0.053 inches, roughly a 20th of an inch. So in 1 second the moon should fall toward Earth by a tiny amount, barely more than a sheet of paper in thickness, while it moves thousands of kilometers sideways along its orbit. When Newton carried that reasoning through and compared it with the actual size and period of the moon's orbit, that tiny drop worked out to be exactly what was needed to keep the moon in its observed path. A number measured by simply dropping objects near the ground predicted how far the moon falls around Earth each second. One law, inverse square gravity, linked 2 completely different phenomena: free fall in your hand and celestial motion overhead. That was the power of a correct law. It let you use one part of the universe as a calculator for another. The same thing happened later with light. Astronomers tracked the moons of Jupiter, especially Io, as they circled their planet. They knew how long each orbit should take if Newton's gravity was right, and they used those moons like precise clocks, watching Io disappear into Jupiter's shadow and reappear. But the timings did something odd. Sometimes the eclipses came several minutes earlier than expected, sometimes several minutes late. The difference wasn't random. When Earth and Jupiter were closer together in their orbits, the eclipses appeared ahead of schedule. When Earth and Jupiter were on opposite sides of the Sun, farther apart, the eclipses lagged behind. The simplest conclusion was that the motions of the moons were fine. It was the light carrying the information about those motions that was delayed. Light did not arrive instantly. It arrived after a travel time that depended on distance. By trusting Newton's gravitational clockwork and treating the moons as reliable, Ola Roma realized that the discrepancy was telling him how fast light must be moving. The farther the light had to travel, the more the events appeared shifted in time. From the amount of shift and the change in distance, he could estimate a finite speed. That was the first solid evidence that light had a speed at all, and not an infinite one. Once again, confidence in one law uncovered another. Now, fast forward. Over centuries, measurement methods got better. Spinner mirrors, rotating cogwheels, long baselines on Earth, eventually lasers bouncing off reflectors left on the moon. All of it converged on the same constant. In modern units, we simply define the meter so that the speed of light in vacuum is exactly 299,792,458 meters per second. It's built into the way we measure space and time, but the really unsettling discovery wasn't the value. It was the invariance. Imagine standing still on a quiet field with a flashlight. You switch it on, measure how fast the pulse races away, and you get C, that 299,792,458 meters per second. No surprise. Now imagine boarding a train that roars along at half the speed of light relative to the ground. Unrealistic for tracks, but fine for a thought experiment. You close the doors, no windows, just your cabin and your flashlight. You point it forward in the direction the train is moving and fire a pulse. Common sense says you should see that light racing ahead at your speed plus its speed, like throwing a ball from a moving vehicle. In everyday life, speeds add 50 miles per hour train plus a 10 miles per hour jog gives 60 miles per hour relative to the ground. Light refuses to play this game. The measurement does not give C plus something. It gives C again. Same if the train is at 90% of light speed, or 99.9%, or 99.9999%. Every time you build the thought experiment correctly, or an actual experiment with moving sources and receivers, you get the same vacuum speed. The number does not cooperate with the rule, this speed plus that speed. It silently demands that you change the rule. Einstein's move was to give up the idea that time and space are fixed backgrounds. To keep C the same for all inertial observers, you must allow time intervals and lengths to depend on motion. A moving clock will tick more slowly relative to a stationary one. A moving rod will be shorter in the direction of motion than it is in its own rest frame. This isn't a trick of perception. It comes out of the Lorentz transformations that replace Galilean ones when C is finite and sacred. Time dilation and length contraction are precisely what make the speed of light come out the same for all observers. Up to this point, everything is still just about cannot quite reach C. If you push on a massive object, its energy and momentum increase in a way governed by the factor gamma equals 1 over the square root of 1 minus v squared over c squared. As v approaches c, the denominator approaches 0, gamma blows up, and the energy required to push closer to c grows without bound. In that sense, infinite energy is needed to hit c exactly. This already tells you that you won't casually accelerate a rocket with mass to light speed. But that still sounds like an engineering problem. Infinite energy could be interpreted as we don't have the right technology. It doesn't yet explain why the universe would treat an actual crossing, going faster than c, as something much darker than just very difficult. The deeper issue is how space-time classifies events. Take any event, say the moment a light pulse is emitted at a particular place. That event divides space-time into three types of regions. Inside the future light cone are events that can, in principle, be reached by signals traveling at or below light speed from the emission. Inside the past light cones are events that could have influenced that emission. Outside both cones, in the elsewhere region, are events that are too far away in space and too close in time, or vice versa, for a light speed signal to link them in the allotted time. For events in the cones, everyone agrees on the order, this cause, then that effect. For events in the elsewhere region, different observers moving at different velocities can disagree on which came first, and there is no absolute correct order independent of frame. That would just be an odd curiosity if nothing real could link those elsewhere events. As long as influence, information, forces, signals never travels faster than c, the fact that some distant flashes of lightning can swap order depending on your motion doesn't hurt anything. They never affect each other. Their relative ordering is like the ordering of unrelated paragraphs in different books, arbitrary but harmless. The trouble begins the moment you imagine a genuine faster-than-light signal. Suppose you have two observers, A and B, separated by a distance of 1 light second in some frame. That means a light beam would take 1 second to cross the gap. Now suppose A has a device that can send a controllable signal to B at, say, 4 times the speed of light. That signal will arrive in 0.25 seconds in A's frame. Mark the emission event E at t equals 0, x equals 0, and the reception event R at t equals 0.25 seconds, x equals 1 light second in that frame. From A's perspective, everything looks fine. A sends, then B receives. Now shift to a frame moving at a significant fraction of c relative to A and B. Because time and space mix under Lorentz transformations, the coordinates of E and R in the new frame will be different. For speeds like 0.8 c, the time coordinate of R in the new frame can easily become negative while E stays at 0. That means that in that moving frame, R happens before E. In other words, what A calls sending first, then B receiving later, some other observer calls B already had the signal before A sent it. That bizarre flip is not optional. It's guaranteed for any influence that connects space-like separated events, because in that region, before and after are not invariant. On its own, that's strange. Combine it with a return signal and it's disastrous. Let B, upon receiving the message, immediately send a reply back to A using the same faster-than-light method. In A's frame, the first message left at t equals 0 and arrived at t equals 0.25 seconds. The return could then be set up so that it arrives at A at a negative time coordinate before t equals 0 when you transform back through the right sequence of frames. It's just a matter of choosing the relative velocities and superluminal speed properly. The geometry allows it. You have built what's called a closed causal curve, a loop in space-time where an event lies in its own causal past. Now give that reply a specific content. Do not send the original message. A receives this command at, say, t equals minus 0.1 seconds and obeys. Then A never sends the first message at t equals 0. But if A never sends it, B never gets it. If B never gets it, B never replies. If B never replies, A never receives the warning and therefore does send the message. There is no consistent story. No assignment of what happened can satisfy all the pieces simultaneously. You have permitted a situation where an effect prevents its own cause. This is the terrifying part that hides behind the polite statement, nothing can go faster than light. Faster-than-light signals are not just faster. They allow the construction of paradox machines. They give you the tools to create information with no origin, a blueprint sent back in time to be used to build the very machine that will send the blueprint back. They threaten the basic idea that the world can be described by a consistent history. As soon as you allow superluminal influence between space-like separated events, and you keep the principle that the laws of physics look the same in all inertial frames, these loops are not rare, they are inevitable. This is where Feynman's style of thinking comes in. He was famous for treating antiparticles in quantum field theory as particles moving backward in time in certain diagrams. That doesn't mean we watch electrons literally reverse age in the lab, but it shows how deeply time symmetry sits in mathematics. When you look at particle interactions on paper, paths that seem to go backwards in time appear as perfectly valid contributions. Nature doesn't cringe at the idea of time reversal in the equations, it cringes at contradictions. As long as processes are arranged so that no real-world observer can exploit them to build a loop that changes its own cause, the universe seems content to allow all kinds of strange time symmetries in the math. Allowing a practical faster-than-light signal would cross that line. Suddenly, the backwards-in-time paths wouldn't just be bookkeeping tricks. They could become channels for actual messages. You could, in principle, send instructions into your own past light cone. And unless some deeper consistency principle steps in, you could ask your past self to behave in ways that undermine the very conditions required for the message to exist. Feynman's warnings about not fooling yourself apply here. If the equations combined with relativity tell you that superluminal signals plus frame invariance yield causal loops, then you can't just shrug that off because you like the fantasy of beating light speed. Could the universe allow faster-than-light travel in some very restricted sense while still protecting causality? People have tried to find loopholes. One idea is that maybe there is a preferred frame, a built-in rest frame for the universe, so that faster-than-light is only defined relative to that frame, not all frames equally. That would break the relativity principle, and we would have to explain why all the countless experiments that test Lorentz symmetry haven't seen that difference. Another idea is that maybe there are hypothetical particles, tachyons, that always move faster than light but cannot be used to send controllable information, or that wormholes and warp-like distortions of spacetime might let you effectively get somewhere faster than light would along the normal route without giving you a way to form a paradox loop. In almost every serious analysis, the same pattern emerges. Either the configuration is so exotic it requires negative energy densities and unstable geometries we don't know how to realize, or it quietly allows the same kind of closed causal curves if you combine it with motion. You can bend spacetime to your will only so far before you run into the same wall. If your shortcut lets you beat a light signal from point A to point B in a way that different observers can chain together into a loop, you've reintroduced the paradox. The universe appears to be designed, or at least selected, to make such configurations either impossible or self-destructive. Put all of this together, and the picture looks like this. The speed of light was first uncovered through gravity's fingerprints, using falling objects and orbiting moons. It was measured more and more precisely, until it became a defining constant of our units. It was found to be invariant across inertial frames, forcing us to accept time dilation and length contraction. That invariance carved spacetime into light cones and elsewhere regions, with C as the boundary between everyone agrees on before and after, and order depends on motion. And the moment you imagine beating that boundary with a real signal, you are not just dreaming of going somewhere quickly. You are dreaming of a universe where you can receive a reply before you send a question, where blueprints have no author, where history can fold back and erase the step that created it. Something terrifying happens if you beat light speed is not a threat about engines exploding at sea. It is a statement about logic. If space-time stayed as we know it and superluminal signaling were possible, the terror would live in the breakdown of causality. That is why, in the end, the safest conclusion is not that some cosmic policeman enforces a speed law, but that the geometry of space-time itself is built so that exceeding CE with information simply cannot happen. The number 299,792,458 meters per second is not just how fast light goes. It is the conversion factor that keeps cause ahead of effect. It is the rate at which now can spread. It is the universe's way of saying, beyond this boundary, if you insist on sending signals, reality no longer owes you a consistent story.